In this video, I'm going to talk about the Moivres theorem. But before I talk about the theorem, let me remind you of a couple of things. Imaginary number I is defined to be square root of -1. Now, if you square both sides, you're going to get I square is equal to -1. Then I cube is going to be I times I square, which is going to be I times -1, that is going to give you -I. So I cube is -I. Then I to the power 4 is I square times I square, which is going to be equal to I square is -1 times -1, that is going to be equal to 1. So any integer power of I is going to give you one of these four values. Okay, it's going to be either I, -1, -I, or 1. Now, let's talk about e to the power x. There are many ways you can derive the value of e to the power x, or in general, in particular, e. However, there is one series expression for e to the power x, which, by the way, is this 1 plus x over 1 factorial plus x square over 2 factorial plus x cube over 3 factorial. I'm going to write out few terms here for convenience, for later convenience. So x to the power 4 over 4 factorial plus x to the power 5 over 5 factorial plus ... Now, just to remind you, factorial of a number, so let's say factorial of 3, or 3 factorial is 3 times 2 times 1 is equal to 6. Or factorial of 4 is going to be 4 times 3 times 2 times 1 is 24. And you get the idea. N factorial is a product of first and positive integers. Okay, so 1 through n. But one special value, just while I'm talking about it, 0 factorial is defined as 1. So we just define 0 factorial to be 1. Now, having said that, this is where I'm going to focus. E to the power x, so is equal to the right side 1 plus x over 1 factorial plus x square over 2 factorial and so on. However, I kind of want to bring to your attention sort of like something interesting. What it says in ordinary people's language. It says that e raised to the power some value x. So e raised to the power some value, whatever value it is, okay, is going to be equal to 1 plus that value over 1 factorial. That value is square over 2 factorial, that value cube over 3 factorial, and so on and so forth. So there is no restriction technically on what x can be. X is a number. It's a number. That's as much as we know. It could be real number, complex number, whatever. So how about if we take this idea and replace x with something like I theta, okay? Where theta is some number, I is the imaginary number I here, square root of -1. So if I do that, what do I get? Okay, so let's go ahead and do that. So I'm gonna replace x by I theta. So every time we see on the right hand side x, I'm gonna have to replace it by I theta. All right, so it's gonna be 1 plus x over 1 factorial, but now my x is actually I theta over 1 factorial plus x square now is going to be I theta square over 2 factorial plus x cube is going to be I theta cube over 3 factorial plus x to the power 4 I theta to the power 4 over 4 factorial plus x to the power 5 is going to be I theta to the power 5 over 5 factorial, and you get the idea, right? Now, if I were to simplify it a little bit, on the right hand side, I'm going to get the following. 1 plus I times theta over 1 factorial plus, now I'm going to stop here a little bit. I have I theta square over 2 factorial, which is going to be I square times theta square over 2 factorial. But I just showed that I square is negative 1, right? So this is going to be actually negative theta square over 2 factorial because I square is negative 1. Now the next one is going to be I theta whole cube, which is going to be I cube theta cube, right? And of course it's divided by 3 factorial. So, but I cube is negative I just showed you here. So it's going to be negative I times theta cube over 3 factorial. So it's going to be negative I times theta cube over 3 factorial. And I to the power 4 is 1, so it's going to be plus theta to the power 4 over 4 factorial. And I to the power 5 is going to be just I, because I to the power 5 is I to the power 4 times I, right? But this is 1. 1 times I is I. So it's going to be plus I times theta to the power 5 over 5 factorial, and it keeps going. At this point, what I'm going to do on the right hand side, I'm going to reorganize the terms. E to the power I theta is equal to 1 minus, so I'm going to combine the terms that do not have i's in them and combine the terms that do have I in them. So the ones that do not have I are going to be this 1 minus theta square over 2 factorial plus theta to the power 4 over 4 factorial, and it'll keep going. Next, I'm going to combine the terms that have I in them. So I times, so theta over 1 factorial. So theta over 1 factorial, then this one is going to give me minus theta cube over 3 factorial plus the next one is going to give me theta to the power 5 over 5 factorial, and is going to keep going like this. The signs are going to alternate. The same here. As it turns out, by the way, this thing is a series expression for our familiar cosine of theta, and this thing is a series expression for our sine of theta. Our trig functions, we define them as a ratio of one of the sides to the hypotenuse of a right triangle. That's how we define cosine and sine. So however, it has a series expression too, and these are the series expression. This is a little bit advanced for pre-calculus. This is something we talk about in calculus too, but don't worry about it. The concept is so simple that it doesn't matter. You can easily grasp it. So now I'm going to rewrite e to the power I theta is equal to cosine of theta plus I sine of theta. And this is called Euler's theorem. Euler's theorem. Now I'm going to take Euler's theorem, which I just derived, and derive the Moivres theorem. So what I'm going to do, I'm going to take this guy and raise the power of this to n and raise the power of this to n, where n is a positive integer. For simplicity, n is a positive integer. So the right hand side, which I'm gonna leave as it is. I don't know what it evaluates to. So left hand side I'm gonna evaluate. So e to the power I theta raised to the power n, using the rules of exponents, this is the same as e to the power I n theta, correct? Thus this thing is equal to this. Now this I can rewrite as e to the power I times n theta, correct? Now this, like the way we kind of described e to the power x, we replaced x with I theta, and then we derived this in exactly the same way. Instead of theta, we are going to assume that it's n theta. The theorem still should hold true, the Euler's theorem. Theta is what? Theta is just some numbers. So is n theta. So it doesn't make a difference. So this is gonna be, using the Euler's theorem, gonna be cosine of n theta plus I times sine of n theta. By the way, this is the same as this, which is this. So look how we went from here to here, and by doing some manipulations we came up to this. So we just showed you that cosine of theta plus I sine of theta raised to the power some positive integer n is actually equal to cosine of n theta plus I sine of n theta. This, by the way, is called de Moivres theorem. So we have started from very basic here. We started off with I, imaginary number that all of you know, right? I square, I cube, I to the power 4, etc., etc. E to the power x is just a definition. You have used e to the power x before, right? But there is a way to define it. There are multiple ways, as I told you, to find out e to the power x value. So this is just one way. So I take e to the power x, and instead of x, I replace it with I theta, and I do the simplification, and I come up with series expression for cosine of theta and sine of theta. From that, I derive Euler's theorem, which is e to the power I theta is equal to cosine theta plus I sine theta. Then I raise the power of both sides of this equation to n, a positive integer. And then the left-hand side, I simplify it to get this expression, which should be equal to the right-hand side. And that leads to the de Moivres theorem. I hope that this discussion was helpful. Thank you very much.